Chapter 15, Part 3. So self-ionization is when two like molecules react to give ions. So in this case, we're talking about water. So two water molecules can react to give the hydronium ion and the hydroxide ion. So if we wanted to write our equilibrium expression, Kc would be equal to my two products over my two reactants, which are just water times water. We include them all because they're all liquid or aqueous phase. So the concentration of our two ions is really, really small. So that means the concentration of water is pretty constant. So what we did is we moved over our H2O squared and we set that whole thing equal to our two ions. And we call this product here, our amount of ions product is called the ion product constant, which is Kw. So Kw is equal to the amount of hydronium ions times the amount of hydroxide ions for water. At 25 degrees Celsius, it's a value of 1 times 10 to the negative 14th. So it's a constant value at that temperature. But if you change the temperature, then it does change because we already know that temperature varies the Kw or the K constant. We can rewrite this also as just H plus instead of H3O plus, since these two things are essentially the same. It's just a matter of adding a water versus taking away water, but the concentrations are pretty much the exact same. So we can just simplify it a little bit and do H plus instead of H3O plus. So using this expression, we can calculate the amount of H or OH in a water sample because we know Kw is always this constant. So if these ions are produced in equal numbers, which we assume to be true for pure water, then X is going to be equal to both our H and our OH. So in this case, Kw so 1.0 times 10 to the negative 14th. We're going to call each of these X because they're going to be the same value, so X squared. So that means the concentration of both of them are the same. 1 times 10 to the negative 7th. So a very small number. So if you have a solution, an aqueous solution where you have an acid, it is also going to contribute way more of this H+. So you can typically ignore the amount of hydrogen contributed just from the water because it's such a small number. So the amount of hydrogen ions is determined only by the acid that you've added. There is a little bit of OH from this self-ionization of water that contributes to the whole solution, but again, it's very small compared to the overwhelming amount of hydrogen from the acid. So if we have a solution, a hydroxide solution, and the molarity of the acid we've added is 0.10 molar HCl. So since we have a strong acid, then that means all of that is going to dissociate. So we're going to have that molarity of H plus ions. So we can use our Kw expression. Kw, again, we're at the correct temperature we're going to assume we are. Our amount of concentration of hydrogen is 0.10 since we have a strong acid. It would be a lot more complicated if we had a weak acid. Times our amount of hydroxide. So we're just going to solve for our concentration of OH. So 1 times 10 to the negative 13th, so very small concentration. If you have a strong base solution, then it's going to contribute the amount of OH, so you can ignore the extra amount of OH from the water because it's so small compared to the strong base. So the concentration is just determined by the base, and there is a small amount of H from your water, but again, it's so small compared. So calculate the concentration of H plus if we have a 0.010 molarity in NaOH. So this is a strong base, so that means we're going to have 0.010 is our OH concentration. So again, our Kw we can plug in our value for our hydroxide and solve for our hydrogen. So if you dissolve a substance into water, you can change the amounts of H and OH depending on what you add to the pure water. If the solution is neutral, then the two concentrations of the ions are equal, whatever they are, but they are equal. In pure water, we know that they're both 1 times 10 to the negative 7th. If you have an acidic solution, that means you have more hydrogen than you do hydroxide. In a basic solution, you have more hydroxide than hydrogen. So you can think of it in terms of concentrations. In an acidic solution, your H plus is going to be more than this 1 times 10 to the negative 7th. If it's acidic, it's going to be, if it's neutral, it's going to be equal to that. And if it's basic, it's going to be less than that amount. So we can quantitatively describe the acidity by using something called the pH, which is just an easier way to get a number to describe how acidic or basic something is. So the pH is the negative logarithm of your hydrogen concentration. So negative log of whatever that concentration is. So if you have a concentration of 1 times 10 to the negative 3rd, you would type in negative, the log button, and then the concentration. In this case, you would get a value of 3. So you typically want to keep as many sig figs as your concentration. So we would want to do 3.0 and keep 2 sig figs. So in a neutral solution, they're equal. So the pH is 7. In acidic solution, you have more than this amount of hydrogen. So your pH is going to be from 0 to usually like 6.9 or up to 7. Basic solution is going to be greater. So 7.1 up to 14 is going to be your limit. So here are some common things and their relative concentrations, and then the pH that you would calculate from them. So typically we label things of pH of 1, 0 to 2 as strong acids, and then weaker, neutral is 7, weak base, and then your strong bases have a pH of 12 to 14. The closer they are to neutral, the weaker they are. So if we have a hydrogen ion concentration, what's the pH? So pH is our negative log. Make sure you put this in parentheses in your calculator. So when you do that, you're going to get a pH of 3.54. So that's a relatively weak acid. Okay. If we want to work backwards, we can do that too. So we know the pH, we want to know the hydrogen ion concentration. So we need to get rid of this log. So the opposite of log is 10 raised to. So we would do 10 raised to the negative log. It's going to cancel out that. So we're going to do 10 raised to the negative 7.40. So when you type this in your calculator, there should be a little 10 near the log button. It's probably like the shift or the second version of it. And you do 10 and you do negative 7.40. And you would get a value of 3.98 times 10 to the negative 8th molarity. We can also calculate something called the pOH, which is the relative amount of your hydroxide ions. We do this for basic solutions. Works the same way. pOH is equal to negative log of your hydroxide concentration. So what's the pH of a 0.12 molar NaOH? Strong base. So this is the amount of our hydroxide. pOH equals negative log and pH does not have units, so 0.92. Now, how do we relate pH and pOH together? Because typically we always convert things to the pH scale and keep them on one scale. That's easier to remember than trying to keep track of both of them. So pH and pOH, their sum is equal to 14. So if the pOH is 2.54, what's the pH of that? pH plus pOH is equal to 14. pH is 11.46. So this would be a basic solution. Not quite a strong base, but not quite a weak base either. An ammonia solution has a hydroxide ion, so this is this. What is the pH of this solution? So there are a couple of ways that you can solve this, but the takeaway is that there's going to be two formulas you have to use either way, because you have two problems. One, you're going to get from concentration to the pH, and then two, you're measured in hydroxide, but pH is hydrogen. So you have to get one to the other. So I'm going to show you both versions. So the first thing you can do for the first way to solve it is to use your KW formula. So KW is a constant. We can plug in my hydroxide value. Solve for your hydrogen ion. And then plug that into the pH formula. And you'll get a pH of 11.3. The other way you could solve it is to plug your hydroxide amount into the pOH formula. pOH, you have OH. And then plug that into your pH plus pOH formula. So pH equals 14. So my pH in this case is also going to be 11.3. So either way you solve it doesn't matter, but you're going to have to do two separate formulas, either your KW and then your pH formula, or your pOH and then your pH-pOH formula. It just depends on which one you would like to do. So the pH can be accurately measured using something called a pH meter. And usually what happens is you just get a readout. But a more common older method is using indicators, which change colors based on their pH values. So they usually have a small range where the color changes dramatically in that small range. So like methyl orange starts out at red at a pH of 3, and then by it gets to almost 5, it turns yellow. So you can kind of see within that window as to what the pH is. But if you're trying to measure the pH and you know it's around 10, it wouldn't make sense to use methyl violet because the pH isn't, it's not going to change in that range. So a pH meter would look something like this, where you just put it in your solution and it would just read it out for you. You wouldn't have to measure any colors, which are kind of subjective because, we all see colors a little differently. So it's a little bit more accurate reading. All right, and then finally, these are all your operational skills for Chapter 15. So make sure you're comfortable doing all of those things before you do your quiz.